Hey, hello, Physics 20s. Sorry, I'm just going to change my lighting here. Um, yes, I'm going to do a quick video on these practice questions in case you need some extra help. I'm going to start basically with question number 3. Um, this one shows this guy on a motorcycle jumping off a ramp, and he's clearing 5 buses. Okay, he wants to clear them with a height of 1 meter with a speed of 15 meters per second at his highest point. Okay, for this question, I know there's a lot of information here. It does say assume that air friction is negligible. So that means it's isolated. And as soon as you know it's isolated, then what you should say is that EM1, the total energy at this that he has at this position, that has to equal EM2, the total energy that he has at this position. Okay. And you'll see that happen in even these other practice questions. So what you start with is you say then, okay, fine, EM1 has to equal EM2. And then what you do is you break up each position into the kinds of energy that it has. So in EM1, like right here in this position, he has some gravitational potential energy because he's got a height number 1 and he's above the ground. So he's got gravitational potential energy. Now he also has kinetic energy. Okay, and I'm going to call that mv1 squared for now. I realize this question really just wants kinetic energy, but I'll show you the full expansion if that helps, okay? So that is, he also has kinetic energy at that point. Then if you look at his second position, here he has mgh2. Sorry, I'm running out of space here. And he also has 1/2 mv2 squared. So up here, he's got a different, well, actually, we know that one. Okay, so what I'm going to do is just quickly show you. We know his final velocity. It's right there. Okay, so that would be V2. He wants to clear the 5 buses by 1 meter, but each bus is, what is each bus? Oh, 3.5 meters. Sorry, there it is right there. Okay. So basically, we've just got to go 5 times 3.5 is 17.5 plus the meter. So height number 2 is going to be 18.5 meters. That's the height that he wants. Okay, 18.5. So anyway, I won't do all the math here, but what I'm hoping you'll see, you need to get the setup here is the hardest part. The math I don't think is too bad. This one does say what kinetic energy does he need to have at the beginning? Well, the kinetic energy that he needs to have at the beginning would be all of this. Okay, so in this case, I'm not going to need to solve for V, but you could. Okay, but effectively, what you have to do is grab this amount carefully. Okay, with H2 being 18.5 meters, and then add that to the second amount, this kinetic energy here, with V2 being the 15. Okay, so I know I'm starting to make this a bit messy here. The point is that we add those two together, and then you would subtract MGH1 from that. Okay, because on the left-hand side you have MGH1. So subtract all of that as an entity. Okay, you got to keep those together, and then you would have EK. All right. So that's a quick tip on these. You can pause this and rewind it anytime you need. Okay, so number 4, classic question. Just identify everything quick as you go through it. So there's a force. It acts on a mass over a displacement up of 4.8. Assuming there's no friction in this movement, what is the change in kinetic energy for the mass? That is carefully delta EK. So this is what I mean. As soon as you see that you have a delta, there's only really one formula that has a delta in it. And I'll re-erase this, but work is equal to delta EK plus delta EP. Okay, so if you can calculate the work done, work is equal to force times distance. I'm simplifying a little bit because I know it's going up, but you have the force and you have the distance up. Okay. So you could calculate the work done. And you can also, like, you're trying to solve for this, so don't worry about expanding it. But the change in gravitational potential energy would be mg delta h. Okay. And your delta H is going to be 80 meters. So you would have risen. I realize you're going to use 80 meters right here and 80 meters right there. No big deal. Okay. Because the change in gravitational potential energy is only part of the total change in energy that will happen, right? Because you're doing work on it. So just raising it alone, you won't need the amount of work that you did so you won't need this total amount of work just to raise you. You'll have some left over, and that will tell you how much kinetic energy you then have. Okay, so that's that one. Again, just pause this as you're going through it if you need to kind of see that real slow. I'm just kind of blasting through these. Number 5, this is a classic one because it's telling you information about this mass in 2 positions. Okay, so it's released from height 1. And it does say it's a frictionless plane. So as soon as you know it's frictionless, we can say that EM1 is going to equal EM2. The total mechanical energy up here is going to equal the total energy right there. Okay. Now, all you have to do is carefully, when you're expanding this, you have to carefully identify what kinds of energy you have in each position. Ultimately, it is saying what's the elastic constant of the spring. Because see, it looks like this mass slides down and it's going to hit the spring at this position, okay? Because if you see this arrow, let me clear that out. This arrow is showing you the displacement x. So the spring was originally up here, and then it got compressed down to here. Okay, so it got squished. Okay, so but you are looking for K. Now I'll show you that K is just going to come out of the wash here when you start expanding the mechanical energy problems. So EM1 at the very top here, because it's released from a height, if it's released, that means it was released from 0, essentially, is what we're assuming. So the only energy that it has in position 1 is mgh1. Okay? It only has gravitational potential energy up here. But then if you look at position number 2, now we're down here, okay, position number 2, right there, it still has some gravitational potential energy because it has a height. Okay, it's not quite to the ground. But crucially, it says it came to a rest. Okay, so it means it doesn't have any kinetic energy. It's not moving. So right at that instant, it has come to it, like it's basically slowed down, came to a stop. So the other kind of energy that it now has, though, because you have now cocked the spring, if you could say it that way, or if you squished the spring doesn't like what you've done to it. Now the spring has a lot of elastic potential energy, which can do something, and it would in a moment if you let the system keep going. But anyway, so that means 1/2 kx squared. Okay. Now, it does tell you what x is. And what you have to be careful of is that you get that into meters. Okay, so just watch that. That's an easy, it's kind of a little sneaky there. But this x will go right here. You know the mass, you know gravity, of course, and you know the height, and you know the mass, you know gravity, and you know this height. So what I'm saying is, when you get this all set up, this is the only thing you don't know. Okay, and so yes, you have to be careful, kind of treat these as mathematical entities because they're all kind of, well, they're all tied by multiplication. So effectively, you would go mgh1 minus mgh2, and then you would keep solving down till you get to k. All right, so I won't show you all that, but hopefully that's helpful as well. Okay, now just 2 more here. This one wants to know the change in kinetic energy again, the change in EK. All right. So If you know this right here, that this mass has this velocity up, okay, that's your initial kinetic energy, EK initial, okay, and that would be 1/2 mv squared. You can calculate that. Then it says a force acts on the mass over a displacement of, sorry, I blocked that out, 65 meters up, okay? So again, if you want the change in kinetic energy of the mass, the only formula that has that is the work energy theorem. It's the only one that's got delta EK, all right? So, actually, it just wants the change in kinetic energy. So this information here at the beginning is not necessarily needed because if you know the force times the distance, that would be the work put into the system. And just like we did in the other question, if it experiences a displacement up, then that means you have another mg delta H, okay? You've changed the potential energy of this mass by a little bit, and we have exactly the same question where you need to solve for the change in kinetic energy, okay? So the change in kinetic energy will be the final amount minus the initial, but it doesn't need you to find the final amount. It just wants to know the change in. So literally you would just take this amount here and minus mgh from that, okay? And you'd get it, okay? So again, I'm just showing you that really fast here. Now this last one, oops. So if we shoot a cannon ball at 245 meters per second at 52 degrees, the cannonball will follow a parabolic path because it's a projectile. So it's going to do something like this. Okay. Now, it says assuming air friction is negligible. That's good. They want to know that means that it's isolated. Okay. So it wants to know the kinetic energy of the cannonball at its highest point. So when you get up here, sorry, I guess the cannonball is coming out. There it is there. I mean, it's obviously going through its whole trajectory. But when you get to the top, if you want to know the kinetic energy that it has right there, that kinetic energy, of course, would equal 1/2 mv squared. Okay. So, and we're assuming that we're shooting this basically from the ground because it doesn't say that there's a height at all. So, see this one, it just wants the kinetic energy at that height. We don't necessarily need to analyze how much energy it had to start with, although that can help you. But really, if the question just says, what is the kinetic energy at its highest point? This is what you need. We already know the mass. We just need to know what the velocity is at its highest point. Now, this one's going to force you to remember that anytime you shoot a projectile, it has a horizontal and vertical component, Vx and Vy. But by the time you get to the top, the only component you have is Vx, okay? Because Vy would equal 0, right? By the time you get to the top, vertically, you're not accelerating anymore. So when this question it's kind of pinpointing not necessarily the need for total energy, although the total amount of kinetic energy that it has here would become kinetic plus gravitational potential energy here, okay? But it doesn't want to know. The question's only getting you to focus on just what is the kinetic energy at the highest point. So your clue is then you just need to figure out what the horizontal velocity is. Because if you remember, that horizontal velocity stays the same all the way through its trajectory. And that is the only velocity that it would have right here at the top. It would only have Vx, okay? So once you figure that out, you plunk that in here and that should get you the answer. So anyway, those are just some helpful tips here. Hopefully that's going to help you guys as you keep reviewing. You can hit me with questions over the weekend. I'll be in and out a little bit, but I should be able to answer some of them. But yeah, if you haven't taken the test yet, which I know a lot of you are still working on review, which is good, we'll have you ready for Monday. So hopefully that's helpful.